Hello, Dr. Julian. Am I audible?
Hello.
Can you hear? Hello. Yes, it's nice to see you after a long time.
Nice
How are
to
you
see you
doing?
again. Good.
All right,
Nice
we
to
are
see everyone
excited
there.
to have you. We are all excited to have you again, Dr. Julian Onions. So we'll be talking about orbital mechanics today. So if you're ready, you can go ahead.
Okay. I need to have screen sharing set.
All right, I'll.
Okay. I think that's, can you see that?
Yes, Dr. Julian.
Yeah, great. So I'm going to talk about orbital mechanics, which if you go on to study that, you'll find there's quite a lot of maths involved and it's quite a complicated topic, but I'm going to try and help you through some of the simpler bits. Now, the big thing with orbital mechanics, which is all about really how you get into orbit and how orbits happen and things like that, we generally think of it with spacecraft. And the problem with spacecraft is they use a lot of fuel. So this is pictures of some rockets, which is what they would look like if you could actually see inside them. So this is the Saturn V over here, and you can see all this stuff here, the red, blue, and yellow is all fuel. So they need a lot of fuel to get anywhere. And this is the space shuttle again, lots and lots of fuel. This bit at the front is where the passengers, the astronauts, live. Again, right up at the top of the Saturn V. And in these cases, these are rockets that put satellites into orbits. So you can see most of it is really fuel. So it's a very difficult thing to get a rocket up into space. If you want to carry more weight into space, then you need to carry more fuel to get that into space. But then you have to lift that fuel up into space too. So you need more fuel for that. So it's quite difficult. Luckily, you can win a little bit by adding some more fuel that will get you into space with a bit more mass, but it's not a very easy equation to manage. The more fuel you put in, the heavier the rocket is, so it needs more fuel. So you can see it just gets a bit complicated. The next thing is if you launch a rocket into space, you might think you can just go straight up and get into space. And you can do that. That there are some companies that offer you that sort of trip if you've got a lot of money. The Amazon one and the SpaceX, not the SpaceX, the Virgin Galactic, both do that. But if you do that, if you go straight up like this, you come to a point where the Earth's gravity is strong, is enough to pull you back because you've run out of fuel. So you start off going up into space, and then you run out of fuel and you just come back again. Now, you can get out of space, get into space like this if you go fast enough. You have to go at a speed of just over 11 kilometers a second. So that's 11 kilometers every second. Once you're going at that speed, you will be going fast enough to get away from the Earth and never come back. Gravity will never be able to pull you back if you can get up to that speed. But that's quite a big speed to get up to, and it's quite inefficient to get to that speed. So usually that's not how rockets try and get into orbit. They try to go sideways instead. So if we could look at this is a thought experiment proposed by Isaac Newton over 400 years ago. So if you have a cannon on the North Pole and you shoot a cannonball and it goes slowly, it's going to end up in the sea. If you send it really quickly, then it will come round the Earth and end up in the sea a bit further. But if you keep shooting it faster and faster, eventually it will go right around the Earth and come back to where it's started. So it will fall as fast as it went. So in that point, it's into orbit. It will never actually come back to Earth. Well, it might do, but that if we just consider sort of a perfect example, it will never come back to Earth. It will just go round and round the Earth forever. And that only needs 7 kilometers a second. So that's how fast you need to get into orbit. You need to be going 7 kilometers every second, which is less than this 11 kilometers a second that you need. So you need a bit less fuel to do this. So that's why it's very attractive to do that as a first step, because you can sort of rest then. You can go into this orbit and you just go round and round the Earth, and that's a nice place to be. This is how the astronauts went to the moon, and how a lot of spacecraft go to Mars and other places. They get into orbit first, and sort of once you're there, then you can rest. You can unpack things. You can put out solar panels to get electricity. You can reconfigure the spaceship and just basically get sort of settled in, and then you can fire a motor that takes you out of orbit and takes you to wherever you want to go, to the moon or to a higher orbit or to a different place. So that's kind of the basics of it. Now, I don't know how much maths you know, and this might scare you, the next bit, but just if maths isn't your thing, then you can skip over this bit. If I can get it to come up. So these are the 2 equations that we use for orbital mechanics. By and large, there are a few others, but these are the 2 principal ones. So this one up here, this is gravitational force, and this was worked out by Isaac Newton in 1666 or sometime like that. So about 400 years ago. And this is another one. This is to do with circular motion. So if you go on to study physics, these are 2 equations that you will become very, very familiar with. So this one says, how strong is gravity, basically? This is the force due to gravity, F. We just put an F there for the force due to gravity. And it depends on 2 things, well, 3 things really. What it is that is out in space. So this is the mass of the rocket, how heavy the rocket is. This is how heavy the Earth is. So that doesn't really change. That's always the same. And this is the distance between the 2. So if you have a rocket here and the Earth here, this tells you with how much force the Earth is going to pull it and try and attract it. This one, on the other hand, says how much force you feel by going round in a circle. So this is dependent on the mass of the rocket, how heavy the rocket is, how quickly you're going, and how tight a circle you're going in. Now, if you put those 2 together, you can balance them and you can say, well, I want the force of going round in a circle to be exactly the same as the force trying to pull me down. So the 2 cancel out. That's when you stay in orbit. So you can put those 2 together and say, well, those 2 are equal to each other if we're in orbit. And then a few things cancel. The mass of the rocket cancels, one of the R's cancel, and you end up with this equation, which tells you how fast you have to go to be in orbit. This is the velocity, how quickly you're going, and it depends on how heavy the Earth is and how far above the Earth you go. But okay, that's a lot of maths, and it might be a bit beyond you at this point. But the important thing here is that this distance from the Earth is on the bottom. So the bigger this distance goes, the smaller this velocity becomes. So you go slower as you go further away from the Earth. And it also takes you longer as you go further away the Earth to make an orbit. So the fastest and quickest orbits are very close to the Earth, and the slower ones are further away. So what else have we got? Yeah, so as the distance goes up, the velocity goes down, or as the velocity goes up, the distance goes down. And this is what makes orbital mechanics very odd. It perhaps doesn't correspond with what you think, maybe. So if you go back to this and say, right, here we have the International Space Station, which orbits at about, I think, 300, maybe 400 to 400 kilometers above the Earth's surface. So it's in an orbit that stays there. It goes round and round and round. And quite often you have to go and they send a new crew up to it. So they have to launch from the Earth and they have to go and dock with it and put the new astronauts on. So when that happens, this is going around like this, going around in a circle all the time. Takes about an hour and a half, the space station, to go once around the Earth. So they see a lot of new days. So if you have a space shuttle like this, so we don't have space shuttles anymore, but we do have rockets that go and visit it. If it's on the same orbit, it will never catch it up because they will both be going at the same speed. So you might think, well, I just go a bit faster. But if you go faster, you will actually come down into a lower orbit. That's the only place you can get faster, is into a lower orbit. So to catch up to the space station, you don't just go faster, you have to move down into a different orbit nearer to the Earth. So that's what they do. They go down into this lower orbit, and now they're going faster than the space station, so they gradually catch up with it. And then as they get closer and closer, they move their orbit up and up and up until eventually they're quite nearly the same orbit. And then when they're very close, they can just make fine adjustments and actually do the docking. But you can see that it's a little counterintuitive. It's probably not what you expect some of the time, that when you're trying to catch something up, you can't just go faster. You have to go into a different circle to catch up with it. So with these rockets, they can't just chase the space station. They have to drop down into this lower orbit and go a little faster. And this is just a table of how long it takes to go around. So if you could go at round at the level of the Earth, which you couldn't, that would be 0 height above the ground, it would take you about 1 hour and 24 minutes to go around the Earth. Where the space station is, which is about 400 kilometers, then it takes about an hour and a half. So if you see the space station go over your house, which you can see, I don't think it's got one coming over Sri Lanka just in the next few days, but there are places you can look on the internet. Just Google ISS transits, and it will give you a time to look up to see the space station go over. But if you see it go over, then it will come over again in another 90 minutes, an hour and a half's time. That's because it's at this altitude. If you go much higher, you can see it takes longer and longer. So at 2,000 kilometers, it takes over 2 hours to go round. Now, if you go really, really high to this particular height of 35,786 kilometers, then the time to go orbit the Earth is now 23 hours, 56 minutes. And that's actually the same rate as the Earth is spinning. It's just less than 24 hours. So if you can put a satellite right at this position, at 35,786, then it stays just above the location on the Earth. And these are very useful places to put communication satellites. So if you want a TV station or something on a satellite, then this is where you would put it, because it would stay overhead your country all the time. If you put it anywhere else, it would begin to move away, and it would come back eventually. But that's not very good if you want to watch TV, because you would watch it for half an hour and then it would disappear. So these are called geosynchronous or geocentric orbits. They're quite a long way out, so you need quite a bit of rocket fuel to get to these positions. But once you've got them there, they will more or less stay there. They sometimes need to be tweaked a little, because nothing in space stays exactly where you put it, because there are other tiny forces that accumulate over time. If it was just the Earth and this satellite, then it would just sit there. But because we're in a solar system with the sun, the moon, Jupiter, they all have a little pull on this object. So sometimes they move it slightly out of position. So these rockets, they have a big, powerful rocket to get them to there, and then they park in this orbit that goes around for an hour and a half, for 23 hours, 56 minutes. But they then have little tiny rockets on them just to nudge them back into the space in case they start to wander off. So that's the sort of thing that you have to learn. So yes, a geostationary orbit at 22,000 miles or 36,000 kilometers about. If you put something there, then it will more or less stay where you put it, and you will always be able to see it. Now, going back to the International Space Station, I said you can see this go overhead in the night sky if you know when to look. And I've seen it quite a lot of times. I've used these apps. You can get them on your phone, you can get them on the internet, you can get them in a web browser, but if you just type in where you are, it will tell you when the next time to see one is. And this isn't exactly what it looks like, but this was a photograph I took out in my garden. And you can see this is the International Space Station. So these are just stars here, these little white points. But I took this for about 30 seconds, and you can see how far the space station moves in 30 seconds. It moves quite a long way. And here's another one that I took. This one is going this way through the night sky. You can see the stars have moved a little bit in this 30 seconds as I took it. But if you just watch it, you'll see a very, very bright star moving across the heavens. On this one too, you can maybe see right at the top, there's another thin trail. And that was a supply vessel bringing new food, water, and oxygen, etc., up to the space station. So this was in a slightly different orbit, going slightly faster, slowly catching it up until it could dock and deliver all the food and supplies that they wanted for the next few months aboard the space station. And the last thing I'd like to tell you about is how do you get to another place? So if you want to get to the moon, I said normally you go up into space and then you go into this orbit. So you settle into this orbit around the Earth as your first section of the mission. Now, you could just then, if you've got a really big rocket and lots and lots of fuel, you could just then shoot off to the moon and go there. But that uses a lot of fuel, and fuel is very, very expensive to get up into orbit. It takes more fuel to get the fuel up into orbit. So it's a very difficult issue to solve. So it's better if you can do a much simpler transfer, which will get you from one place to the other. And this is called the Holman Transfer orbit after, I don't know what his first name was, but Holman was the one who worked it out. So this is the cheapest way you get from one place to another, is get one of these transfer orbits. So you start off in this orbit where you're going around and around the Earth. And then at some point you fire the engine, usually at about this point here, when you're furthest away, to speed up the craft. And rather than push you into a bigger circular orbit, you go into an elliptical orbit, ellipse or an oval. And here you can see, so this is now a much bigger orbit, and if there was nothing else happening, you would just go off on this orbit. You go all the way around here, all the way around here, and all the way back again. And you would completely go around this orbit forever, unless you did something else. But if you time it just right, then as you come up to this point, the moon, which is also in orbit, will be coming round here, and you would just catch up to it as it arrives. So that this is often how they do it. If you want to go to Mars, it's a very similar thing. You go into one of these big elliptical orbits, and you aim to go to the place where Mars will be when you get there. So with an orbit like this, it takes about 3 days to get to the moon. So when you fire your rocket, you're going to this point here. The moon will not be here. The moon will be perhaps way up here somewhere, but it will be moving along here and slowly coming into position. So 3 days later, when you get around here, the moon will be right in the right place for you to be. And then generally what you do then is fire a braking rocket and slow you down and take you into an orbit like this one. And then you're captured by the moon and you're into the moon's orbit. So this is what the Apollo astronauts did. They, when they went to the moon, they went up. Apollo 8 was the first one to do this. They launched here, went into this orbit here. They checked out everything was okay. They went around a few times, made sure everything was perfect, because it would be much easier to get back from an orbit here if there was anything wrong than out to the moon. And then they said, okay, got the okay from mission control. They said, yes, you can go. They fired their engine on the third stage of the rocket and gave them this boost. And then they switched it off, probably about here. and they just drifted on this orbit for 3 days. Drifted. And then as they got closer and closer, they could see the moon, and then the moon's gravity pulled them in. And if they didn't do anything, they would have gone right behind the moon and come back to Earth. And they sort of did that on purpose. Well, it's a lucky event, but it's also very useful, because if something does go wrong on the outward thing and you find that you haven't got enough food or enough oxygen or water, or something goes wrong and you can't make it, then you don't really have to do very much. You just go around the back of the moon and you'll come back to Earth. So this was indeed what happened on the Apollo 13 mission, where they were about this far in their mission when they had a big explosion on the spacecraft, and they had to do a lot of very quick work to save the spacecraft from sort of blowing up and save the astronauts. But then they hadn't got very much left at this point. They couldn't fire the motor on the rocket because that was damaged. So luckily they just moved along in this big orbit, and then they didn't do anything special at this point, and then just came all the way back to Earth. It took a lot of clever people on the ground to get them to last that long, because they'd lost a lot of oxygen, they'd lost a lot of power, they'd lost all sorts of things on the spacecraft. So they had to be very creative. And there's a very good film about it. If you haven't seen the film Apollo 13, that covers that story very well. So that's sort of orbital mechanics, and it's very similar for nearly everything you want to do. If you want to go to Mars, you do the same thing, but you fire the engine for a lot longer, and you have a lot longer ellipse. But again, it goes all the way out to Mars, and you just have to calculate it right, so that when you get to the highest point of this oval, Mars is where you want it to be. And then you get to sort of this point, fire your engines to slow you down, and then you get captured into this orbit here. And then from there, if you want to go and explore Mars or something like that, if you're a Martian explorer, which some of you may well be, by the time you grow up and finish school, they may well be asking for astronauts to go to Mars. And so one of you could be that astronaut. But anyway, you'll have to work all this out. Luckily, we have computers that can do a lot of this hard work for us. You just tell them what you want to do, and it can work all that sort of thing out. So that's all I've really got time for today, unless you've got a few questions, but I hope you found some of that interesting. It is a very complicated subject, quite a lot of maths in it, but quite rewarding when you get to it, because you can work out how to move around the solar system with very little effort. So something that you might well be involved in maybe later in your career. NASA and quite a lot of other places. There's SpaceX, there's China, India, Israel, have all launched rockets to different places. And the list is growing every day. So by the time you've left school, I imagine there'll be lots of jobs for people who want to work out how to fly spacecraft and the best way to do things. So thank you very much
for that. Thank you very much, Dr. Julian Onions. So let's keep it short, kids. So if you all have any questions, we just have only a few more minutes because we're in a tight schedule. So if you all do have any questions, please make sure to ask it briefly so that Dr. Julian Onions could give you a short answer. So is there anyone who wants to ask any questions? No questions?
Very good.
All right.
I hope I didn't frighten you too much with the maths. That was perhaps a little advanced stuff, but maybe you'll remember it in the future when you study physics at a deeper level. But it's basically just balancing these two forces, that you have an outward force and an inward force, and you get them to balance, and that's when you get into this nice orbit. And from that, you can work out all these other things.
All right, kids. So thank you very much, Dr. Julian Onions, for that wonderful session. So it was really informative.
Thank you
for really informative, and thank you for your time.
Yeah.
Thank you for your
perhaps,
time, and it
see
was
you.
really wonderful to have you again after a couple of weeks. So hope
Yeah.
to see you again too very
Yeah,
soon,
hope to
Dr.
be
Julian Anians.
hope to be back again, and best of luck to all of you in your studies.
Thank you, Dr. Julian.
Thank you.
See
Goodbye.
you. Have a nice day. Bye.
Bye, Dr. Julian. Bye.
Bye bye. Have a good day.